Hello everyone, welcome to the course on architectural design of ICs. So, we are basically discussing the power reduction methodology for low power VLSI design. So, we have seen that clock gating is used for dynamic power consumption reduction, and then we have used some of the, that means static power reduction technique to reduce the, that means the leakage power. Now, actually if we see the comparison of, because with the recent days actually this technology scaling or this voltage scaling, the leakage power will becoming major part of this contributed to the overall power consumption over the dynamic power. So, to see that, actually if you see the corresponding ITRS roadmap, so you see that this green color line is the actually this dynamic power consumption, whereas this leakage power consumption, they are basically actually overpowering or with this dynamic power consumption. So, actually day by day if I see that, okay, with this technology scaling, how this leakage power and dynamic power are becoming effective in the major power contribution is that in 250 nanometer technology, the leakage power is very much small or it is very much trivial in compared to the dynamic power consumption. But with this 65 nanometer technology, you see actually this it is coming almost half of, that means 50% contributed to the leakage power as well as the dynamic power consumption. So, with the recent actually activities, this is up to 65 nanometer technology, with the recent actually 3 nanometer technology or 7 nanometer technology if you see. So, at the time major contributor will be the leakage one rather than the dynamic power consumption. Okay. So, that is why this leakage power reduction we can use this power gating technique. So, what is there actually in power gating technique is that the basic strategy of power gating is to establish two power modes, active mode and low power mode, and switch between these power modes where it is necessary. The establishment of these two power modes is a pragmatic remedy for accurate switch between these modes at the appropriate time and in the appropriate manner to maximize the power savings while minimizing the impact on the performance. And therefore, switching and the controlling process is also becoming complex. So, due to this power gating implementation, there may be three modes of operation: the active mode or the sleep mode or the wake up mode. That means, actually what we are discussing is that nowadays actually if your mobile is in use, so at that time it consumes the power more, that means at that time you are using the dynamic power consumption is more, but whenever your device is not used for, let us say, for a long time, so at that time the major power contributor is the, or major power consumption source is the leakage power. So, if you can reduce this leakage power, or if you can put that, okay, and nowadays actually if you see the laptops are also coming like that, or if your phones are also like that, if you are not using the phones or if you are not using the laptops, so at that time after certain period of time, let us say 10 seconds or 1 minute, the laptop or phones got into the idle mode, the display is also shut down, some of the that means the processing blocks also they are getting shut down. So, why? Because whenever they are not in use, then why to supply the power to each of these modules? So, that is why if I can create three mode, that means whether there is active mode or wake up mode or the sleep mode. In sleep mode means it is in the low power mode. That means the system is like whenever we are like we sleep, so at that time our body part is basically working, okay, but it is like in the dormant state. So, it is the dormant state which we provide in the circuit level itself. So, whenever it is not in use, so the minimum number of, that means minimal voltage will be applied to the each of these particular device, that means the corresponding circuits or to the corresponding gates. Okay. So, that is why this power getting things we can apply whenever to reduce, we need to reduce the corresponding leakage current or this leakage power. So, actually the sleep transistor is that this is head sleep transistors. Okay. So, that means within this logic block I am having one transistors which is basically connected with the VDD extra transistor, which is this connected with the VDD. That means, whenever this mode is in, suppose if this is coming as okay, that the corresponding it is in active mode, at that time the VDD will be connected to the logic block. If it is in the sleep mode, so at that time it will be just open, there will be no VDD connection connecting to the corresponding logic block. So, this is the that means head sleep transistors, and for foot sleep transistors it will be connected with the ground. That means, at that time there will be no such connection to the corresponding ground. Okay. So, that is why that means here this particular things, this is the virtual power at that time, this is the virtual ground at that time. So, depending on putting these sleep transistors at the ground power supply as well as the ground, now I can make or I can activate whenever they need, otherwise it will be in the sleep mode to reduce the corresponding power supply. Then the another actually technique is that switch sizing. So, smaller switches means smaller area, large capacitance, large resistance and good leakage reduction. So, bigger switches requires larger area, but smaller resistance and relatively low leakage reduction. So, that is why we will use the switch. If I can use the switch, smaller switch, then I can reduce the corresponding reduction in the leakage in a great extent. So, how in a cell, how you can place the switch? So, switch transistor in each standard cell, area overhead is a disadvantage and physical design easiness of EDA is an advantage. So, that means in every of the standard cell, now I can place these switch transistors to make it, that means to reduce the corresponding this leakage power consumption. So, then we are having here, this is the grid of switch which we already placed in between this that means the corresponding standard cell based design. So, grid of switch says that okay, switch placed in an array across the power gated block and 3 rails routed through the logic blocks. Why this is connected? Because the virtual grounds or the virtual power we have to create to make every of these blocks are like power gated. Then the switch placing architecture, how we can place the switch. Okay. So, you can create the ring of switch by putting them actually vertically as well as that means horizontally. So, the horizontal line will be the virtual supply and this is the that means global supply, and in between of them, in between of this standard cell you can place the corresponding switch cell. So, low, that means smaller switch cell, very good reduction in the leakage. Then actually we can do is that signal isolation. So, what is the signal isolation? Powering down the region will not result in crowbar current in many inputs of the powered up blocks. None of the floating output of the power down block will result in spurious behavior of the power up blocks. Clamps will add some delays to the propagation path. So, what we are doing actually, some of the that means blocks, if they need that signal to be isolated. So, at that time we can put this AND gate by with this particular enable signal, which is this isolation, okay, and then they will provide to the corresponding particular gates to reduce the corresponding power consumption. So, the power gating has different modes. The power gating modes are basically 2, fine grain power gating and the coarse grain power gating. So, in fine grain power gating, the process of adding a sleep transistors to every cell is called as fine grain power gating, And in coarse grain power gating is that implementation of grid style slip transistor to stack of logic cell which drive cell locally through the shared virtual power network is known as coarse grain power gating. So, in coarse grain power gating we are having this ring based and the column based. So, we have to switch actually whatever we have seen that we have to place the switch. So, we have the ring. So, this is the coarse grain power gating, and another thing is that every of the cells if it is power gated. So, that is fine grain power gating. So, the two actually techniques you can, for a complex circuit you cannot apply this fine grain, that means each of the transistors is power gated. So, at that time it will create too much of overhead, because we are putting some of the resistor and the controller part will be also much more complicated at that time. So, then the controlling mechanism for this is that non-state preserving power gating, the cutoff, multi threshold, then boosted gate, then super cutoff. The other one is that state preserving power gating is that variable threshold, zigzag cutoff or zero delay ripple turn on. State preserving use some retention resistor to store the corresponding states. So, that means these are the controlling what I said is the power gating technique or the power gate, that means the transistors or the slip transistor whatever we put, whether that is head or tail. So, depending on that we have to control them, that okay, if this is in slip mode then you please disconnect the power line or disconnect the ground line from the main block. So, something like that we have to actually we have to do this power gating control mechanism for this this particular cells which we use depending on different type of, which is this cutoff, multi threshold, boosted gate, super cutoff. So, there are several other ways to control this particular transistors. So, then state retention technique is that when power gating taking place we have to retain some critical state content or FSM. So, software based register read and write, scan based approach based on using scan chain to store state of chip or the retention registers. So, these are all actually the power consumption method, and then this retention registers. What does this retention registers says that when power gating taking place we have to retain some critical registers content, and saving and restoring state quickly and efficiently is the faster and power efficient method to get the block fully functional after the power up. There can be various methods for state retention. In DSP unit, the data flow driven DSP unit can start from reset on new data input, and the cache processor, this mechanism is good for large residual state retention. Means what, actually whenever we are basically powering up the system design. So, at that time in DSP what we can do, you can use the reset signals to basically get the new value or the to retain the corresponding value in the registers, or in processors we can use the cache memory to retain the corresponding state of the each of these particular registers. So, now then again another thing is that, so how you can do this synchronous and asynchronous logic power gating. So, clock gating for dynamic power reduction, which reduces the power consumption of ideal selection of synchronous circuit. Asynchronous circuit has an inherent strength of data driven capability and active while performing useful task. Asynchronous circuits implement the equivalent of a fine grained power gating network. Power gating can be efficiently implemented in pipeline flows. Okay. So, that means all the synchronous circuit as well as this asynchronous circuit we can apply this clock gating as well as the power gating, whereas this asynchronous circuit they can be much more, they will be much more useful for actually power gating, or their controlling mechanism for this power gating in asynchronous circuit, that will be much more simpler than the asynchronous circuit. Okay. Then we need to verify the power, like whenever actually we do the this digital circuit design. So, at that time we run some formal verification or some verification method. to check that okay, if I apply this stimulus, then at that time what will be my that means expected output. If it is matched, then we can say that okay, we are getting or we have designed the proper design. Okay. So, we do timing analysis, we do everything to get or to know that okay, my design whenever it will comes in the physical form, at that time it will work perfectly fine, but still there is a huge gap between the or real time performance and the virtual performance of my chip, but still which creates the yield, but still actually we the people try to make the gap very much closer, so that the virtual virtual performance it really or nearly close to the actual performance or the real time performance of my circuit design. So, just like this actually this formal verification which we do in the digital circuit design. So, we have to do some power verification method too. So, in the power verification process in the EDA is consisting of the steps of analyzing, monitoring and validating power rules related to EDA tools. Means what? So, at the time in the EDA tool, so that is the automated process. So, in the EDA tool we need to consider that okay, so that in which particular region I am consuming of my whole chip, which region I am using most of the power. So, if I find that okay, the memory is consuming, suppose inside in processor design the memory is consuming much more power or the video processor is taking much more power. So, at that time I will try to consider how I can apply different technique to reduce the power consumption on that particular block. Why? Because in the complex nowadays this complex system design there will be so many sub blocks. Okay. So, if I IP based design, so many IPs are connected. So, among them which IP contributes to how much power in the overall power budget of my system, overall system. So, that I have to know and identify, and then according to that I can take the necessary steps to reduce the power consumption to that particular block. So, that is why we need one power verification tool, so that the tool automatically does the power actually information it will provide to me, and depending on that particular report now I can take my decision or I can take the steps against the corresponding report. So, that is why this each and every of this power estimation and the reduction rule and the algorithm should be test and check against the digital cores. It is essential to have verification process in the EDA development cycles to ensure that the software infrastructure is working properly for electronic prototyping. Okay, so, another point is that still now actually we are basically working or we are talking about hardware, but there actually I need one perfect actually systems to be work perfectly fine. I need the perfect softwares too. So, if you are suppose one laptop you are using, if there is no such operating system, so at that time you cannot use the laptop. Whenever you put the operating system, then only your that means you can work, or your that means whatever hardware is there. So, that is useful for you at that time only. So, that means software is also one of the major part which controls your hardware. So, that is why whenever we have done everything like okay, we have done this enable signals and all these things, but ultimately there will be the control will be in the hand of the softwares. That means, whenever the device will be in the that means idle mode, how the device will know that I am not using or the any process is not running on the processors. So, that is the job of the softwares which will say that okay, if this particular process is not running in a laptop or in a mobile phone or in any electronic system. So, at the time you put that thing in the sleep mode. So, that activation signals or the control signal will come from the software part only. So, that is why we have to the verification process along with the software part and the hardware part, both are together. Actually, we need a verification to that okay, everything is running fine. That means, whether we will put the hardware under the software. So, at that time it is working, or the power consumption whatever we are claiming that okay it is reduced or it is increased or it is something else. So, at that time it is work perfectly fine. Perl and C++ is the language which we use to write the script, and then HDL, hardware description language, the Verilog and the VHDL is used to generate the test vectors or the test case. So, power actually to verify that means what will be the power, actually I need the test vectors. Why I need the test vectors? By applying the test vectors I can get the corresponding actually switching activity of all the signals, all the nets which are present in my system. So, whenever this all the switching activities information I stored somewhere, and then if I give that switching activities to the tool, then only it can calculate that okay based on these switching activities or based on these particular simulations, that means based on this particular test vectors, this is your that means activity, and this is your power report of dynamic power consumption or the leakage power consumption or the switching power consumption or the that means glitch power consumption, if there is a glitch. So, glitch power consumption, every power information at that time it will provided to you once you run the simulation and provide that particular that means the all this switching activity file to the power simulator. So, now how actually you can this verification of power monitors. So, these power monitors where all mathematics and physics comes to engineering. So, suppose consider that A and B nets have simulation data. So, C does not have a simulation data. So, at that time this depending on this, now this verification how we can do, just like in simulation what we can see that okay we are having some applied some of the inputs which will come as the that means the waveform. So, here also if we can see that okay how much power I consumes in terms of actually this waveform, that will be very much easy to interpret the meaning of the corresponding power signals or the power consumption. Okay. So, the power monitors is that, so depending on this A and B signals, for this particular case depending A and B is the two inputs how they are changing, and depending this is the switching activity of A and B. So, depending on this A and B signals, so how this C is changing and how this C is basically contributing to the major power source, that we will see through the power monitor. So, here in power monitor some correlative or partitioning approach is needed, and power monitor is the solution for checking or for interpreting the power consumption in a digital circuit in a very simplified way, and divide the simulation time into fastest clock slots and find the probability for each and every portion and integrate them together. So, that means how we calculate the corresponding power is that we find out the activity rate as well as the probability of, that means how much time the signals will be high. So, depending on the activity and the probability both together we can estimate the rough, that means we can roughly estimate the power of the overall block. And why actually here why is it is the integrating of the integration of each of these block means what, for each of these signals what will be their probability and their what will be their activity rate, based on that, based on this particular equation, now they are trying to find out the power consumption report. So, the future trends of this this power consumption this methodology and the EDA is that there will be one physical aware power reduction, and then there will be some way to fix it, leakage reduction with advanced power getting techniques, asynchronous power pipeline microarchitecture, then neural network approach for design automation, and neurosynaptic computing. So, these are the future trends of power and actually this power reduction techniques in VLSI design. So, the first thing is that physical, actually in every steps of VLSI we need the power should be reduced, whether that is we are in actually device level or whether we are in the, that means the logic level, or whether in the system level. So, every level we will try to minimize the power consumption by applying different techniques. So, it is not that in EDA actually for designing the complicated circuit nowadays we need the help of EDA, that means the process will be automated. So, at that time if we can develop some of the physical aware power reduction and then the fixing methodology inside of the EDA tool itself, then the leakage reduction with advanced power getting option like this strong ODC or strong HDC options embedded with the EDA option, EDA tool, along with the asynchronous pipeline architecture. As we said, the synchronous, instead of synchronous, asynchronous circuit are they are more low power application, they will be applicable for more low power application, or they can achieve more low power. And then the recent trend is that neural network or the artificial intelligence applied on the design, electronic system design automations. That means, if I find that okay, this is the artificial intelligence means what actually, if I can experience that okay, this is the previous situation I get, okay, at that time I have used this power getting of up to let us say 60% to the overall circuit. So, at that time if I find the same situation, so at that time without considering anything, again I will apply 60% power getting at that time to the overall circuit. And then we are having this neurosynaptic computing, which is again the emerging this artificial intelligence or the neural network approach, and the neurosynaptic computing in the EDA tool for this power reduction or this to area optimization or to this speed enhancement, all this to make one efficient circuit design. All are the recent trends in the this VLSI design tool in the electronic design automation aspects. Okay. So, with that this is the end of this this power, this is the power actually reduction techniques. There are many, and still people are trying to, as this is the future trend. So, still people are trying to improve the techniques to which will be applied for reducing the power to a great extent. So, with that, this is it for today. Again we will see some other topic in the next class.